One of the most profound jokes of nature is the square root of -1 that Erwin Schrödinger had to put into his wave equation in 1926. That is a real quote from the legendary physicist Freeman Dyson, and honestly, it sounds completely absurd, doesn't it? You're trying to describe the absolute fundamental building blocks of reality, the actual stuff that makes up you, me, and the device you're looking at right now, and then you realize, wait, to do this accurately, I literally have to introduce imaginary numbers? It sounds crazy, but this single joke of nature changed science completely forever. Welcome to this explainer. Today, we're going to dive right in and see if we can demystify this ultimate mathematical mystery together, the Schrödinger wave equation. We'll explore the elegant, almost magical logic of how this one single piece of math unlocked the entire atomic world and laid the absolute bedrock for modern physics. Here is our roadmap for today. First, a quantum joke of nature. Then, the Schrödinger equation itself. Third, the meaning of the wave. Fourth, trapped particles and standing waves. And finally, solving the hydrogen atom. All right, let's jump straight into part one, a quantum joke of nature. You know, it's actually amazing to think that this massive scientific revolution started with a totally casual challenge at the end of a physics seminar back in early 1926. The topic of the day was Louis de Broglie's radical new theory of matter waves. A physicist named Peter Debye casually remarked to the room, well, if matter is a wave, there should be a wave equation. Debye pretty much promptly forgot he even said it. But sitting right there in the audience was Erwin Schrödinger, and let me tell you, he took Debye's casual little challenge very, very seriously. What's truly breathtaking here is the sheer speed of how this unfolded. I mean, late 1925, Schrödinger retreats to a cabin in Arosa, Switzerland, specifically to crack this exact wave mechanics problem. By early 1926, Debye throws down his seminar challenge, and within that very same year, 1926, Schrödinger formally publishes the groundbreaking equation. He literally reshaped our entire understanding of the universe almost overnight. Which brings us to section 2, the Schrödinger equation. To really grasp why Schrödinger's work was absolutely necessary, we just have to quickly compare classical and quantum physics. Classically speaking, if you throw a baseball, Newton's laws give you a definite, predictable trajectory. You know exactly where it's going to land. But down in the quantum realm, things get weird fast. We're suddenly dealing with matter waves, complex functions, and probability densities. The old rules simply didn't apply. We needed a completely new framework to handle a reality that was inherently fundamentally uncertain. And here is the core of that new framework, the time-dependent Schrödinger equation. Simply put, it's a complex partial differential equation that describes the state of a quantum system as it evolves over time. Now notice it contains the imaginary unit, I, the square root of -1. The ultimate irony here? Schrödinger actually hated this at first. In a letter to Hendrik Lorentz, he called the use of complex numbers unpleasant, indeed objectionable. But that little I is exactly what transformed this from a standard, boring heat conduction equation into an entirely new dimension of physics. So how do we actually go about solving something this terrifyingly complex? Well, turns out there is a brilliant mathematical maneuver known as the separation of variables. It goes like this. Step 1, you assume the potential energy doesn't change over time. Step 2, take the wave function and separate it out into an independent space part and an independent time part. Step 3, this trick beautifully, elegantly splits one massive, seemingly impossible partial differential equation into two totally solvable ordinary differential equations. Let's see how this actually builds. By separating out that time component, we are left with the time-independent Schrödinger equation. What we have on our hands now is a classic eigenvalue problem. In simple terms, a mathematical operator, the Hamiltonian, acts on our wave function and it returns that exact same function multiplied by specific, distinct energy levels. This is absolutely massive because it suddenly brings order and completely solvable mathematical machinery to the chaotic quantum realm, giving us what we call stationary states. Moving right along to section 3, the meaning of the wave. Now, I want you to really think about this for a second. What exactly does the wave function mean physically? I mean, we're calculating this complex, imaginary wave for a piece of solid matter like an electron. But what is actually waving? It's not a physical wave of water. It's not a sound wave. So what on earth is it? As it turns out, the wave function itself, which we denote by the Greek letter psi, has absolutely no direct physical meaning. You literally cannot measure it. But if you take the absolute square of that wave function, This is called the Born interpretation. You get the probability density, and this gives us the definitive probability of finding a particle at a specific position and time. The math doesn't hand us the physical particle on a silver platter. It gives us the fundamental blueprint of chance for that particle. The legendary Richard Feynman summarized it beautifully with this vivid quote: "Electron waves are probability waves in the warp and woof of uncertainty." I just love that phrasing. We aren't mapping out solid objects anymore. We're mapping out the precise likelihood of an object existing in a specific spot at a specific time. Next up, Section 4, Trapped Particles and Standing Waves. So before quantum mechanics came along, classical physics had a fatal, glaring flaw when it came to atoms. If you picture the atom like a tiny solar system, you've got electrons orbiting the nucleus. But classical electromagnetism strictly says that an accelerating charge, like an electron moving in a circle, must constantly radiate energy. If it radiates energy, it loses momentum. And if it loses momentum, it should instantly spiral and crash right into the positively charged nucleus. Under classical physics, matter as we know it simply shouldn't exist. We literally shouldn't be here. And here is exactly where Schrödinger's math saves the atom. If we think of the electron not as a little planet, but as a probability wave trapped by the electrical potential of the nucleus, everything changes. The wave reflects back and forth inside this trap and interferes with itself. Now, only specific wavelengths survive this interference to create a constructive standing wave. Because the wave is a standing wave, it is completely stationary. The charge distribution isn't moving or accelerating. And since it's not accelerating, it doesn't radiate energy, perfectly preserving the atom. Which leads to another mind-blowing revelation: energy is quantized. Think of it like a guitar string that can only play certain fundamental notes based on its exact length. An electron wave can only exist in a specific set of distinct energy levels. Why? Because only certain, precise wavelengths can perfectly fit into that potential well to create a standing wave. If the wavelength doesn't fit, the wave basically cancels itself out, and that specific energy state simply cannot exist. Let's bring it all together in Section 5, Solving the Hydrogen Atom. Up until now, we've mostly been talking about one dimension, to keep things simple. But to model the actual hydrogen atom, the exact stuff that makes up stars and oceans, we have to expand our math into 3 full dimensions. We have to transition the Schrödinger equation into spherical coordinates to accurately factor in the central electrical pole of the nucleus. Now, I know the spherical math looks incredibly intense, but amazingly, we can conquer it using that exact same separation of variables trick we saw earlier. We substitute the 3D wave function in, divide both sides by the wave function, and separate the variables out, but this time into radial and angular parts. By doing this, we systematically strip away the complexity until we're left with an effective 1D time-independent equation. It is mathematically beautiful. And this brilliantly illustrates the ultimate payoff. Notice how those abstract, purely mathematical energy eigenvalues we were calculating earlier manifest perfectly here as the actual physical energy states of the atom, E1, E2, E3, and so on. The pure abstract mathematics flawlessly predicts the physical measurable reality of the atom. Seriously, it is hard to overstate the colossal impact of Schrödinger's work. By resolving a totally casual debate about matter waves using a mathematical trick involving imaginary numbers, Schrödinger handed us the definitive blueprint for the entire chemical universe. This single equation forms the absolute bedrock of all modern chemistry and quantum physics. It literally explains how elements bond, how materials behave, and how the entire universe is glued together. Which leaves us with this final, somewhat unsettling thought. Take a look at your desk. Look at your hands. If the most fundamental building blocks of our universe are ultimately just complex probability distributions, trapped as standing waves governed by imaginary numbers, how solid is the reality you see around you right now? It's a completely mind-bending concept, and I really hope this explainer sparked your curiosity to dive even deeper into the quantum world. Thanks for learning with me today.